All right, I'm going to give some people a couple more minutes to flow in if they'd like. All right, let's get going. So, quantum error correction and mitigation. We've been discussing how we're in this NISQ era. We don't have many qubits and we can't maintain coherence on these qubits for very long. So what that means is that we need ways to mitigate that error, which means to try to correct for that. And then there's actual quantum error correction or fault tolerance, where we're actually correcting the errors that occur as they come up. So that's what we're going to get into. So there's a couple things to understand with quantum error mitigation. One is the sources of noise and how we model those. There's mitigation techniques such as zero noise extrapolation, readout, so you can have correlation matrices, probabilistic error correction, dynamical decoupling. These are all strategies that exist to mitigate the noise that your quantum circuit experiences. And these can be applied individually or oftentimes in tandem because they are better at correcting for different kinds of errors. There's also transpilation. So transpilation is kind of a strange word that a lot of people aren't familiar with, but this is what that Qiskit IBM runtime does for us. And remember that we're developing these quantum circuits that are an abstraction. They're a way for us to understand what we're doing, but the real quantum hardware oftentimes uses a different set of gates, and we have to also realize that we can only entangle qubits that are directly next to each other on the quantum computer, and so it has to do swap operations to move these qubits around. That transpilation step is a step where we convert the abstract quantum circuits that we've developed to that specific hardware. And this is also a necessary thing because as we iterate with quantum computers, we have different hardwares with different capabilities, but this allows us to develop one quantum algorithm with a quantum circuit, and then allow the transpilation step to translate that to different hardwares. During that transpilation, you can specify how much optimization you want it to try to attempt. Just like in traditional computing, that 2 knots commutes into a wire, The same things happen with our gates in our quantum circuits, that oftentimes there are combinations or reorganizations that we can do to improve the efficiency and how many gates we have. Um, we'll also talk about the impacts that this noise has on AI and DS workloads. Um, and then after we discuss these aspects, we're going to go into actual true error correction. So this is things like toric codes or bicycle codes and other methods where we allow the qubits to correct each other. And this is oftentimes when people talk about fault-tolerant quantum computing on the vast difference between these physical qubits versus logical qubits. So for true, like error corrected, you may need 7 or 9 or 12 physical qubits for each logical qubits, and that is the big hurdle that we're moving towards fixing as these quantum systems expand. Right now, 12 qubits per logical qubit is kind of a too high a hurdle. Whenever you have 135 or however many qubits to work with, that means you're only left with 10 qubits if you do a fully error-corrected system. So, with the exception of the smallest ones, we're usually using these error mitigation techniques, zero noise extrapolation or things like that. But it's an active area of research on these error correction techniques. One is that as we create more efficient and effective error correction techniques, we can use more of them on the smaller quantum computers, and also that way we're ready as these quantum computing hardware advances so that we can deploy these error correcting codes. So oftentimes when we're developing our algorithms, we're making ideal assumptions. Each gate works perfectly well. There's infinite coherence. These states don't degrade over time. And that our measurement is correct. Grover's algorithm, which is the search of an unstructured array, in the ideal instance, mathematically is proven to have square root of n complexity. But in real situations, as the depth grows, this noise erases the advantage. It replaces our clear result with just static uniform noise. So as we add more and more of these multi-qubit gates like CNOTs, we more and more quickly accumulate these errors. In the earlier session, someone asked about Shor's algorithm and factoring, and that's a huge impediment to Shor's algorithm being able to factor these large numbers, is because while we have proven the algorithm, we don't have the hardware to execute it yet, especially with the noise that we would have to face. The average error on a CNOT on IBM devices is between 1 and 2%, and it's really easy to have 50, 100 2-qubit gates in a quantum circuit, especially whenever you look at that transpiled circuit, when it's optimized for the hardware and we have to apply a bunch of swap operations, which are another kind of 2-qubit gate, to move those qubits around. That error starts to accumulate very quickly. So a big factor on any quantum circuit that you develop is you're going to spend a lot of time on how do I mitigate error, how do I minimize the depth of my circuit. So oftentimes you're making trade-offs where you understand that perhaps repeating this part of your quantum circuit 3 more times would give you a more clear answer, but you're deciding if you can either afford the noise, if you can make the circuit shorter, less deep, and get a reasonable answer, or whether you have to add error correction to it. So there's several different kinds of noise. There's classical noise and there's quantum noise. So with classical noise, that's things like heat and electromagnetic radiation. These are things that affect the state of a qubit, a circuit, whatever the case is, and that's the reason that these quantum computers are housed in massive refrigerators that take them down to 10 millikelvin. It's the reason they're in electromagnetically shielded containers. We're trying to prevent the environment from entangling with these circuits because that eliminates what we're able to extract from them. There's also some quantum noise where there's an aspect of this that will never be truly overcome because quantum circuits or quantum particles have quantum behavior where there is a inherent source of randomness. So error correction and error mitigation is never going away from quantum computing. But some of the specific sources of noise are relaxation and dephasing. These are both collectively known as decoherence. Earlier we talked about that block sphere. Those rotations around the equator, around that z-axis, are the phase. And there is a tendency for the particles to fall out of phase over time. And then decoherence, that relaxation, where the one state at the South Pole has a tendency to relax or fall back to the zero state, to go from an excited state to a ground state. Another aspect is coherent errors from gate control. I've mentioned I'm not a quantum physicist. I don't work on the hardware side, but we are doing these rotations to these particles or in our superconducting chip with typically some type of photoelectric, microwave pulses, laser pulses of different kinds. And we're trying to do exact rotations. So we're trying to rotate this particles, from, the North Pole to the equator, a pi/2 rotation. But, slight errors in how much that's rotated can accumulate. It may be that, we're turning it by pi plus 0.0001/2. And those accumulate over time. They are continually recalibrating the quantum computers, to try to correct these pulses to get this as close to the stated value as possible. And then there's the stochastic errors, these Pauli flips, the X, Y, and Z. That's the quantum probabilities I talked about, that quantum particles and quantum behavior does what quantum behavior does. When you get into a more mathematical view, we won't go into it here, but we can describe this with like what are called Krauss operators, which are just purely descriptions of this noise. And this is often how we determine how much noise we expect our circuit to have. We have these noise levels characterized. How much noise we expect adjacent qubits to impart to each other, how much noise is introduced with each 2-qubit gate, with each rotation, and we can model that to determine how likely we are to get the desired answer out of the end of our quantum circuit. So there's several noise models. You have this Pauli channel describing these bit and phase flips. We have the polarizing channel. That's the basically this is a probability of an error times the identity matrix over the number of qubits. There's a T1 and T2, that relaxation and that dephasing model. And then the coherent over rotations, where our gates don't quite change the state of that particle in the exact amount that we'd like. Error scaling. 1 to 2% error per 2-qubit gate is significant, and you have to correct for that in all but the smallest quantum circuits. In this example, for if I have 6 qubits and I have 8 2-qubit gates, my success drops to almost nothing. So this has a huge impact on like AI and data science workloads, where oftentimes we're trying to use very, very large circuits. It's nothing to have a circuit that's 50 qubits wide and 100 qubits deep, but that's going to decay into basically nothing unless you have some level of mitigation and transpilation in place. Mitigation and transpilation. So zero noise extrapolation is interesting because what we do is we amplify the noise in order to understand what zero noise even looks like. So instead of running our circuit one time, we run it in multiples. We run it 3 times, we run it 5 times, we run it 7 times. And what we do is we create plot points that we can fit a curve to extrapolate what this would look like if there was zero noise occurring in the system. Readout mitigation. This is another source of noise that I didn't talk about a lot, But even the measurement is not error-free. And so with that, we have these calibration matrices that we can use to try to correct for that. There are probabilistic error cancellation, where we provide inverse noise operations. Earlier I talked about how there's errors with a gate. We can provide that gate, and then it's inverse to try to cancel out certain errors. Dynamical decoupling, crosstalk is a huge issue with noise in quantum computers. We do an operation on one qubit, it happens to be next to the other one, and it infers noise into the qubit that wasn't supposed to receive that operation. All right. So during times when that qubit is sitting idle, we sit there and we do what amounts to these canceling operations. We apply an X gate and then another X gate. So 2 knots in a row turns out to be the same thing, but that's a valid way to try to overwrite that crosstalk. So these error mitigation techniques, though, are not getting us to fault tolerance. They're mitigating steps. We're just trying to make it not as bad as it can be. What that makes it do is that we have to take more shots. We have to sample the quantum circuit more times to be more sure of what we're doing. It increases our runtime, and it also is going to increase the variance of the readout. With quantum computers, we're generally getting probabilistic readouts. And so more variance in that, reduces our certainty on what this solution is actually supposed to mean. Transpilation, okay? We take our logical qubits, our abstract circuit, and map it to the physical, while hoping to reduce our depth and our errors. So there's noise adaptive mapping. Not every qubit has the same error rates. Some qubits are more highly connected, some have higher error rates. We can try to map our qubits that need the most connection to the physical qubits that are most connected to following, other qubits. The routing is the insertion of these swap operations that we can apply entanglement to qubits that aren't physically next to each other on the quantum computer. There's also the decomposition to native gates. Each quantum computer has a universal gate set, a set of gates that it can use to recreate all the possible gates that we could use. And so we have to transition, we're using, say, Hadamards and C-naughts and controlled Z's and swap operations and all these other things. And perhaps that quantum computer actually only has 3 or 4 actual gates that it uses in its universal gate set. So we have to, during transpilation, it has to be converted to that. Then there's optimization, which is that merging or commuting of gates to try to reduce the likelihood of error. And there's 3 levels of transpilation. There's 0 to 3. 3 is the most exhaustive. It does the most work to try to make your circuit as compact and error-free as possible, but calculating that's expensive and takes time. Now, true quantum error correction. This is what people are talking about when they talk about fault-tolerant quantum computers. We're moving from the mitigation steps that we're taking, like zero noise extrapolation and probabilistic error correction, to an actual fault-tolerant. That is where we have sets of qubits that are correcting errors that occur as they occur. We're going to talk a little bit about the fundamentals of it. How we are going to use like stabilizer formalisms and Steen codes and other things. Now, error correction is a huge opportunity for research. Many of the internships and jobs that I'm seeing now are focused on error correction. As we're trying to move towards a fault-tolerant quantum computation era, we need researchers and algorithmicists that are identifying and implementing new codes that can have the possibility of correcting these errors as they occur with the lowest budget of physical qubits to logical qubits possible. So we apply error correction in our classical computers regularly. There's various parity schemes. So you encode a single bit, a classical bit, 0, as 3 classical bits. What this does is it squares the probability of you having an error. because to have an error, you'd have to have 2 bits that flip instead of just 1. So we encode 0 as 0, 0, 0, 1 as 1, 1, 1, and we're able to have them basically vote. So, you know, as long as we have 2 zeros, we're going to assume it's a 0. It's not as simple in quantum computing. We haven't talked about this yet, but there's something called the no cloning theorem. And this has to do with, we've talked about how whenever we measure a qubit, it collapses to either 0 or 1. We can't clone a complex state that's a superposition because we can't measure it to see where it's at. So since we can't do that, we have to try to find ways to entangle these circuits together and apply the same operations to them as they proceed to try to identify and correct these error codes. So there's a single bit flip code. You know, it's very similar to the classical code. We take a single logical qubit that's in the 0 state and we triplicate it, and then we do a measurement on the z-axis, that north and south axis, on the z1, z2, and z2, z3. And we can detect if that bit has flipped. There's an issue though, is that that's only detecting bit flips, and with quantum computing, we're not only worried about whether it's closer to 0 or closer to 1, but also that phase. That way we can use interference to do the interesting quantum computation things we can by using interference to explore the possibility of the search space, such that the answer that we want raises in amplitude and the one that we don't decreases. So with that, one of the first error correcting codes is the Shor code. It uses 9 qubits to correct x, z, and y on any single qubit. So with the Shor code, we're dealing with 9 qubits to 1. Stabilizer formalism, all right? The stabilizer formalism is a way of describing how these things are changing and for the error to be corrected. We basically align these qubits that way. If one of them disagrees with the other, they correct each other, all right? And these are these where we apply these stabilizers such as z rotations on qubits 1 and 2 and 2 and 3. That way, if there's an error on one of the qubits, it flips both the syndromes. It flips that state of the qubit. The Steen codes is a little bit more compact. It only uses 7 qubits to correct single errors. Toric and surface codes. I've included a little bit about this in the notebook that I've posted in the text channel for this, but we're using lattices, or grids of these connected qubits, and what we do is we have these qubits existing in this grid such that we have a physical qubit next to a data qubit, or an ancilla, and so we have a qubit that we have data, and we have error correcting qubits that are laid out in this grid: data qubit, error correcting qubit, data qubit, error correcting qubit, so that they can work together to stabilize each other across distances. With these toric codes and surface codes, we are finding ways such that we're decreasing the error threshold to we're moving towards fault tolerance. That is that, yes, we still have error occurring in our systems. We still have bit flips, phase flips happening, but the quantum computer is correcting these things as they occur, such that we can have long-running circuits on quantum computers without it devolving into noise. And that's our little session on error mitigation and error correction. I know we have a mix of beginning members and more advanced members, and if anyone feels like they didn't pick up a lot of that, it's a lot, and understanding all these principles can take plenty of time. But think of this as a chance to expand your vocabulary. This isn't the first time now that you've heard of a Steen code, of a toric code. You understand that these are ways that we encode our qubits such that we can correct the errors as they're occurring, so we can run our quantum circuits for longer and more complex operations. All right, guys, do we have any questions? while Romy's typing, IBM has an entire course on quantum error correction, how that works with examples and walkthroughs. So the logical and the physical qubit. Okay, great, great. So a logical qubit is that I'm sitting on my laptop and I'm writing up my quantum circuit to, try to predict whether this image is a cat or a dog. And I've gone through the logic and I want these things to do this. Now, the difference between that logical qubit and the physical qubits are that if I'm using error correction, I'm going to be representing my logical qubit as perhaps like if I'm using the Steen code, I'm going to be using 7 qubits to represent that. So whenever we're talking about the difference between the logical qubit and the physical qubit, the logical qubit is the little circuit that you draw on your laptop in your program. The physical qubit has to deal with both how many real qubits on the quantum computer we're using to represent that, as well as like, hey, how do we have to translate the gates and stuff in our systems? How do we have to insert the swaps to make this work out? So it's a matter of the abstraction that we deal with whenever we're writing our program in Qiskit, and then translating that into, okay, so if I had a perfect ideal quantum computer, I would just need these qubits. However, given that error exists and decoherence exists, I need to use more than the qubits I have to represent it. So the logical qubits has to deal with if I have an ideal system, what is it that I need to do? Whereas the physical qubits are how many real qubits do I need, in the real world to make this happen. Any other questions? All right. Yeah. No, error correction is its own really interesting things. Okay, so the idea with error correction isn't to identify the errors. It's about identifying them and flipping it. So, if to give the analogy to the classical system where we just take a single bit and we make it 3 bits and have them vote, error correction includes that voting and fixing. That like, hey, we got a measurement of 0, 1, 0. We're going to now correct that to 0, 0, 0 because we're doing that majority voting system. So error correction isn't just about identifying when errors occur, but also changing the system back to the way it's supposed to be. Okay, how do you test or verify if the error correction is working in a real situation or experiment? That's a great question. There's a lot of ways that we can do this. One is that we understand what our rates of error are for each operation we do on a quantum computer. We test this. For measurement error, we let a wire sit idle for a time and then measure it and make sure it's 0. We set it to 1, let it sit for a bit and make sure it does 0. We do these rotations and do the measurements. We know how it should behave, and we measure the error that actually occurs. What that allows us to do is that we can then create a noise model of our system to where we understand how this works, and we can then import that noise model. We can run simulations with that noise model with and without our error mitigation or error correction techniques. Now, that's usually a big error mitigation step, And it's so hey, I designed my algorithm. This is what I want. I simulate it on an ideal simulator that performs exactly the way it should. Takes much longer than one on a quantum computer, but at the same time, I'm able to simulate, exactly how this should work if everything was perfect. Then I add the noise and I observe how much the error it seems to be occurring. Then I test it with my error mitigation techniques. Now, with the error correction, a lot of times what we're doing is we're using those same principles of entanglement and interference to correct the errors as they occur. That is that, we have 9 qubits representing this qubit, and we're allowing them to interfere with qubits that fall out of phase to return them to the state that they're supposed to be in. There's a lot of math and a lot of physics and, the nitty gritty of how this works, but we do have how this noise occurs and at what rates it occurs characterized. All right, so correction by voting is limitless. If one day we get a quantum computer with several thousand qubits, bringing back to the original state of the system will be the same with 10 qubits, for example. I'm not quite certain I understand exactly where you're going for there. But I will say that we have these error correcting codes that have very, very low error rates when we're dealing with somewhere between 9 and 12 physical qubits per logical qubit. So it's one of those things where it seems that we're dealing with somewhere on the order of a factor of 10. That for a logical qubit, we're going to need 10 physical qubits. Because we have to detect and correct for errors in the X, Y, and Z axis with that. So it's similar to the classical voting scheme, but we also use the quantum principles of interference and entanglement to apply those corrections. Okay, cool. All right, everyone. Thank you, everyone, for coming out. Happy Friday. Couple points of business. One is I've been screenshotting and writing down the names of the people who are attending live and in session. But if you guys will do me a favor and just click on that Google Forms link and say that you attended this session, that's a little bit less bookkeeping that I have to do, and I'd appreciate it. We're going to continue having events over the weekend and these recordings. As I said in the last session, please attend when you can. I would love that, but also I understand that weekends are busy. Give those videos a watch when you have time, and I'll set the deadline for watching those videos to Monday sometime. But thank you all very much, and I'll see you all tomorrow. Discord day tomorrow. I'll be hanging out on Discord, helping you with your hackathon projects, answering questions. Looking forward to working with you.